Hello, this is Math 2115 coming to you from the College of DuPage. And the title of this lecture is More Proof Tradecraft. And as always, I encourage you to be an active learner as you watch this video. The first new type of proof we're going to talk about is called a proof by contradiction. A proof by contradiction establishes P implies Q by assuming the hypothesis P is true and that the conclusion Q is false. And then, using what we're assuming here, we derive a contradiction. This is sometimes called an indirect proof, and the contradiction is listed as R and not R, which always is false. And that allows us to conclude that Q is true. Now, this can be understood by saying, if we say that we have P and not Q, and we work through to get a contradiction, this truth column is the same as the original truth column. So you see this is a valid way to proceed. Let's look at an example, and a very famous example. This is the proof that the square root of 2 is not rational. In the history of math, this was very important. Someone was actually killed for discovering this. And there is, to my knowledge, only indirect proofs of this fact. I have never seen a direct proof that the square root of 2 is irrational. The proof we're going to talk about is the proof that's found in Euclid's Elements, which was written around 300 BC. So here is the proof. So what we're trying to prove is that the square root of 2 is irrational, so we're going to assume that it's not. So we're going to assume that the square root of 2 is equal to a rational number, and the definition of rational numbers tell us that it's the ratio of P over Q, where P and Q are integers, and we can insist that these are that P over Q is in its lowest terms. That means there are no factors common between the numerator and the denominator. So that means that if we assume the square root of 2 is P over Q, then we can square both sides, getting this. And do a little bit of algebra and we get this. So we have that P squared is equal to 2Q squared. But that means that since P squared is even, it's a multiple of 2, one can infer that P is also even, and that means that P can be written as 2m. So we're going to take this equation right here, and we're going to substitute instead of P 2m, and we'll get 4m squared. So we have this, but that reduces when the first is equal to the last one. That's 2q squared is equal to 4m squared, and if you divide both sides by 2, we have that q squared is equal to 2m squared. That means that q squared is an even number, and by the same logic we had before, that means that q is an even number. And that means that p and q are both even, and that contradicts the fact that they didn't have any common factors. This is a little bit subtle, maybe a lot subtle, and so you want to think about this a bit. While you're thinking about this, though, I would like for you to use the idea of a proof by contradiction to address this problem. So we're taking an ordinary deck of 52 cards and we're splitting them into two equal stacks, S1 with 26 cards and S2 with the other 26 cards. Suppose that there is a suit in which S1 has at least 9 cards, and the suits are diamond, hearts, spades, and clubs. You are to prove that there is a suit in which S2 has at least 8 cards. Here's another interpretation of that, but that's really what you're trying to prove. You know what to do. Let's see how you did. So here is a proof by contradiction. Suppose there is a suit in which S1 has at least 9 cards. There are 13 cards in each suit, so if this has at least 9, then in S2 there is the most 4 cards in this suit. Now suppose then, by way of contradiction, that S2 has at most 7 cards in the other 3 suits. And you see that is the negation of this statement. So these 3 suits contain at most 3 times 7 or 21 cards. So these 21 cards, together with these 4, only account for 25 cards in S2. Since it contains 26, that's a contradiction. Therefore, there is a suit in which S2 has at least 8 cards. A special case of proof by contradiction is this one. Suppose we give a proof by contradiction of P implies Q, and that means we're saying P implies Q and not Q, and we deduce not P. In effect, we've proven this because not Q was in the hypothesis. So that means that we've really proven this. This is a special case because this is a proof by contrapositive. This statement and this statement, as you recall from the earlier chapter, are logically equivalent. Let's look at an example here then. I'm going to prove this by the contrapositive. So suppose Z is an integer. We're to prove if this expression is even, then X is odd. It's easy to prove using the contrapositive. So we're going to assume that this is not true. So we say suppose that X is even. Then, so we're assuming this is not true, then we want to show that this is odd. You see, we're showing that negation of this will imply the negation of this. So since we're assuming X is even, we can write X equal 2A for some A in an integer, and we plug it in to this expression. And we do quite a bit of algebra. And we come down to this piece, and we realize that this is the same thing as having 2 times 2A squared minus 6A, and 2 times 2 is 4 plus 1. So you see this is 2 times a number, an integer, and so that means that this part is even, so plus 1 is odd. So you see what we've done is we assumed not this, that X was even, and we showed that this is odd. Now sometimes in math, the contrapositive is more useful than the theorem, and I'll give you an example of that too. In calculus, there's a nth term test for divergence of an infinite series, and divergence means it does not converge. So here is the nth term test for divergence. If the limit as n goes to infinity of a sub n does not equal to 0, then the summation from 1 to n of a sub n diverges. Now this test is typically proven in contrapositive form. That means we have the if part and the then part, but we say if this converges. So it's if the negation of this, then this limit is equal to 0. Now, the fact that the limit of a sequence an, these terms approaching 0, does not necessarily imply that the series itself is convergent. And we're going to show that using a counter example. Here is an infinite series. That's what the dot 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 means. And so this is 1 plus a half plus a third plus a fourth plus a fifth, and so on and so forth. It never ends. Now certainly as this goes along, the terms get closer and closer to 0. They're of the form 1 over n. And as n gets large, that gets very close to 0. But we know that this expression is going to be bigger than or equal to, the 1 is the same and the half is the same, but here instead of 1/3 I'm putting a 1/4, and instead of these terms I'm putting a 1 over 8. You see I'm replacing those terms with something that is smaller. But then I'm going to regroup this just by, actually I'm not changing the order, I'm just changing the grouping. So I'm going to group these two together, and I'm going to group these four together, and so on and so forth. Now notice that each of these, this is a half, that is a half, that is a half, that is a half, plus dot 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 means it never stops. So you see this is 1 plus a half, a half, a half, a half. So this thing is bigger than that, and that means this is 1/2, and I can do that as many times as I want. So this sum here, this finite sum, is greater than 1 plus k times a half for any k I want. That means it diverges. And this was developed by, I think he was a French monk in 1350, and it was a highlight of medieval mathematics. The next kind of proof we're going to talk about is called proof by cases. And this is used when the original hypothesis naturally divides itself into various cases. Sometimes the number of cases to prove is finite and not too large, so we can check them all one by one. That type proof is called an exhaustive proof. Computers, with their great calculating capability, provide an opportunity to do larger exhaustive proofs. Here's what I'm going to ask you to do. Use proof by cases to prove that the absolute value of x plus y is less than or equal to the absolute value of x plus the absolute value of y for all real numbers, x and y. This is a proof by cases, and this theorem is known as the triangle inequality. You know what to do. We'll see how you did in the next video.